Hey, what's up? Welcome back and glad to see you again. Today we are going to talk about heat treatment, in particular quenching. So steel is an interesting thing. Sometimes it could be soft and formable, but sometimes it could be hard and also have higher strength and toughness. And we are using heat treatment to alter the properties. And by doing heat treatment, we are actually changing the solubility of carbon in air with certain temperature. And most likely, we want to improve the strength and the hardness of steel. And we call that process as quenching. So in the last video, we discussed iron carbon steel. So if you have not watched the last video, so watch the last video first. And in this iron carbon diagram, we have different phases, such as ferrite phase here, pearlite, it's about here, and on the right, it's cementite, and at the top, it's called austenite. And this is equilibrium diagram. So when we do heat treatment, in particular quenching, so we are dropping the red, hot, high temperature steel suddenly into cold water or oil. By doing this, the strength and the hardness of steel can be improved. So this is still our equilibrium diagram. So we are going to heat up the steel into the austenite zone, then suddenly drop the hot red steel into cold media. In this process, steel is originally in the structure of body-centered cubic. Then we heat it up into austenite area. There are more carbon and iron in the cell, and it turns out to be the structure is face-centered cubic, which has more carbon and iron elements in the cubic. Then we suddenly drop the hot red steel into cold media, and finally get Martensite, and the structure becomes body-centered tetragonal. So in order to do quenching, to get the certain hardness and the strength, we must follow the three criteria. So first of all, we have to heat up to the austenite temperature range, and also the steel must have sufficient carbon content. Most likely we use 0.6% minimum carbon percentage. And also we have to take a rapid quenching. So let's look at one by one. So first is called austenitizing, which means we have to heat up the material into the austenite temperature range, and it will change from a body-centered cubic to face-centered cubic. Then the diagram, equilibrium diagram, tells us what temperature we must heat up to with a certain carbon percentage in order to get the face-centered cubic structure, such as if you have 0.76% of carbon percentage, then 727 degrees C would be enough. However, if your carbon percentage is lower, let's say 0.5%, then you will need to have a little bit higher temperature in order to get into the austenite range. So we must heat completely into the austenite range in order to form Martensite. And the next criteria is the minimum percentage of carbon. And usually we use 0.6% as the minimum percentage in order to be able to form 100% of Martensite for a moderate thickness of sections. However, if the part is thin, then the minimum carbon percentage could be a little bit lower, possibly as low as 0.4%. if we employ rapid quenching techniques. And if the steel has alloy elements in there, then the carbon requirement could be even lower. So this is the minimum carbon percentage. The last criteria is rapid cooling. So instead of the equilibrium diagram, in order to perform rapid cooling, we have to be in the non-equilibrium condition. So for quenching, we are not going to be in equilibrium conditions. So for the equilibrium condition diagram here, it's for slow heating and slow cooling. And we use this diagram to decide heat treating temperatures for hardening and softening, such as in austenite region, the minimum temperature has to be 727 degrees C. However, in non-equilibrium conditions, on heating, the result is going to be almost identical with equilibrium ones. However, for cooling, the result is going to be completely different. And we use non-equilibrium cooling to harden or strengthen the material. So in order to form martensite, we have to apply rapid cooling. So from face-centered cubic to the austenite region, which is face-centered cubic, when we suddenly drop the steel into cold media, the air matrix wants to return back to the equilibrium body-centered structure like this, but it can't. It finally becomes body-centered tetracnol structure. And the additional carbon atoms, they were trapped into the structure. And thus distorted crystal structure like this, and we call it as body-centered tetracnol structure. And we call this structure as martensite. So we just talked about non-equilibrium condition. Then how fast do we have to cool the steel? Well, TTT diagram tells us the time requirement. So TTT diagram is short for time temperature transformation diagram, and also called isothermal transformation diagram. So we use TTT diagram to predict quenching reactions in steels. So this is TTT diagram. It tells us we have to heat up to certain temperature, which is austenite region. So for TTT diagram, the x-axis is time in second, then the y-axis is temperature. And the TTT diagram tells us we must heat the material to the austenite region. Then when we cool the material, in order to get 100% of martensite, most likely the cooling rate has to be within 1 second or 2 seconds. So within those 2 seconds, the temperature has to be able to drop from 760 degrees C to 93 degrees C. So martensite actually start to form at about 204 degrees C and complete at about 93 degrees C. So from 760 degrees C to 93 degrees C, the whole process has to be completed within about 2 seconds in order to form 100% of martensite. Otherwise, if you are in about 10 seconds, then you are going to form the combination between austenite and pearlite. And if the cooling rate is even slower, then it's going to be 100% of pearlite. So if the TTT diagram tells us the quenching has to be within 2 seconds, then we have to use a severe quench. And the rate of quenching depends on the fluid media as well as the degree of agitation. And for fluid media, we could use water quenching or oil quenching, and it could also be molten salt. So it's molten salt and not salt solution. It also could be gas quenching, and water quenching is the most severe one, and the gas quenching is the least severe one. And oil quenching usually has less than half of quench rate than water quenching. And if we add more salt, which is sodium hydroxide, then the cooling rate could be even higher. And also violent agitation can improve the cooling rate as well. And for quenching, the slower the quench and the less chance to get material distortion. However, if the quenching is too slow, then we may not be able to get the desired hardness. So this is about quenching. So in order to form martensite and get the desired hardness and strength for carbon steels, so we have 3 criteria as we have discussed. So first of all, we have to heat the material into the austenitic temperature range. And also we have to have sufficient carbon percentage, which usually to be at least 0.6% of carbon. And also we have to use a rapid quenching technique. And this is all we have for today's video. Thanks for watching. We'll see you next time. Bye.